inverses. When we talk about inverses, you may remember inverse operations. Those are operations that undo each other, right? Like, what's the inverse of addition? The inverse operation for addition is subtraction. What is the inverse operation of multiplication? Division. And so we've been doing this for a while. When we think about functions, we can think about inverses as a function that somewhat undoes another function. So in first period, we talked about these two. Do you guys know how to convert from Celsius to Fahrenheit? Y'all don't know this formula? No? Or we could do this one that converts from Fahrenheit to Celsius. These undo each other, right? So we could kind of think about these as inverses of one another. One, we plug in Celsius, we get out Fahrenheit. The other, we plug in Fahrenheit, we get out Celsius. They are inverses of each other. And we use them in different ways. Like if I were over taking a trip and I was somewhere else and I didn't want to turn my smartphone on because it costs way too much money, and I was trying to figure out the temperature. If I was in Europe, are they going to use Fahrenheit? And is Celsius going to make much sense to me? No, it doesn't. So I would do the conversion in my head to figure out what the temperature is going to be like and determine what to wear that day. Do y'all do that when you travel? Oh, that's another way to do it. She just goes outside.
That's what I do here.
If you're looking,
I just like the work
it's like what's going to be tomorrow.
Yeah.
Thank you. Yeah, exactly. All right. I know. Well, when we were traveling this summer, it can get pretty hot in Pompeii.
Oh my gosh, yeah, Greece can be
Mm-hmm. So, all right, here we go. So, inverse notation. This little negative 1 is telling us this is the inverse of f of x, or f inverse of x. So when we talk about the inverse of the function f of x, this is how we would symbolically denote that. Got it? All right, so here we have a function. F of x equals 2x minus 6, and we're going to find the inverse. It's quite simple. This is a linear function, right? Yeah. So linear functions are pretty simple to start with, but all you have to do is switch the x and y. And f of x means y, right? So we'll switch the x and y, and we'll solve for y. So what do? We add the 6. And divide by 2. So that's all you do. You switch the x and y and you solve for y. We do want to note that it is the inverse, so we're going to use that inverse notation. So instead of y equals, we could say f inverse of x equals, whoops, I left out the little negative 1. Or I could have written this 1/2 x plus 3, couldn't I? Both of those mean the same thing, right? Okay, so now let's take a look at the graphs. First I'm going to graph the original function, f of x. We know it's a line. The line's going to cross the y-axis at -6. The slope is up 2 over 1. Okay, and then we sketch in the line. Go red. Almost there. Yeah, pretty good. Okay, I'm going to switch colors now, and I'm going to graph this inverse.
This will be
Yeah.
confused about. I understand, like, but then you went to the f to the inverse of x and all that. Like, I'm confused on all that stuff. Right after x plus 6 divided by 2 equals y, I got confused.
All I did was I took the y, and I was trying to show that this right here is the inverse of what we started with. So you just use the inverse notation, which is that f with a little -1. So this is showing that this result right here is the inverse of what we started with. Yes, sir?
Well, since they both equal y, why don't they equal the same thing?
No, 1 equals y, 1's the inverse of it.
So still.
Okay, no, this is f of x. I substituted it in the y
Oh.
so that you didn't have to leave the f of x in there. If you guys left the f of x, if you switched it and you wrote an f of x here, that would mess you up. So that's why we just sub in the y.
And up there where it says the inverse of x, your little notes up there, what was the rest of that sentence? I'm taking notes.
There's a couple of different ways we could say this. We could say this is the inverse of f of x, or this is f inverse of x.
Okay.
Yeah. And if they didn't give us f, if they gave us y, we would just say y inverse. Or if they gave us g of x, we would say g inverse. Okay. So it just depends on what we're given to start with. All right, so now once we've switched the x and y and solved for y, and then all I did right here between here and here was substitute f inverse of x to show that this is the inverse of our original function. Okay, now we're going to graph it. So we go up to 3, and our slope is 1/2. And then we'll sketch in that line. Wow, that's beautiful. Okay, so this is the inverse. This is the actual function here. What do you notice about this graph? Yes, ma'am.
Where did you get like the 1/2 and the +3?
X divided by 2 is the same as 1/2 x. 6 divided by 2 is the same as 3. I just divided it by 2. What do you guys notice about those two lines?
The blue one is reflected.
Yeah, the blue one is a reflection of the red one. It's a reflection over what? What line? Y equals x. Excellent. It's a reflection over y equals x. Why is it a reflection over y equals x?
I don't know.
You don't know?
Do you know?
I do know.
That's good.
That works out pretty well, doesn't it? It's a reflection over this line because what did we switch, guys? The x and the y. And so when we switch the x and the y, it's a reflection over y equals x or x equals y. Pretty cool, huh? Yeah. All right.
It's a standard line.
Okay, then I have two more things I want to add, but I didn't want you to see
So
them.
it's the inverse, so it would be a reflection
Okay.
over that.
So, now let's take a look at this red line and this blue line. Don't start. I should have. Let me undo that. I didn't want to done that early. Sorry.
Looks like it's a
Okay, so look at the original line, f. F is the red line, the original line. Is f a function?
Yes.
Yes. How do you know from its graph that it is a function?
There's never a repeating x.
You're correct. And what do we use with just graphs to tell if a graph is a function? Anybody remember the vertical line test, the vertical line test? Does f pass the vertical line test?
Yes.
Yes. So the function f is a function. Is its inverse a function? Does it pass the vertical line test? Yes. So we have a graph and its inverse are both functions. And when we have that, we would say that this function is said to be one-to-one. One-to-one is a special name for a function whose inverse is also a function. So if both the graph and its inverse are functions, then it's said to be one-to-one. Good thing to write down. You look tired today. You're zoning on me.
Confused. So how would, give me an example of an inverse not being a function. How would that look? Would it just like...
I'm actually about to turn that question right around on you.
I don't know how it would look. I don't even know how you got to this point.
Okay, so what did we use for the function? We used a vertical line test, right? And then for its inverse, aren't we switching the x and y's? So what do you think we would use on the original graph if we wanted to know if its inverse was a function?
Horizontal.
Yes. we use the horizontal line test. So, yes. All right, so if you only have the graph of the original function, you can use the horizontal line test to determine if the inverse is also a function. So if you have a graph and it passes both the vertical and the horizontal line test, well, horizontal line test is just like the vertical. If you can draw a horizontal line and it passes through no more than 1 point, then the inverse of that graph is a function.
So you have the regular graph that you start out with. And
Vertical. Yep.
And then you do the vertical and the horizontal line test
Right.
for it?
On the regular graph, you do vertical to tell if that graph is a function. Then you would do horizontal to tell if its inverse
Okay.
is a function. So if a graph passes both the vertical and the horizontal line test, it is a function. Its inverse is a function. Therefore, it is considered one-to-one. Okay. Now, are all linear functions one-to-one?
No.
You're right. There is an exception. What's the exception? Horizontal line. The horizontal line is the only linear function that is not one-to-one. The other line that is not is obviously the vertical line, because the vertical line itself is not a function, right? Okay. Okay, so let's look at this one. Is this crazy-looking swirly-Q a function?
Yes.
Yes, it passes vertical, right? So, is f a function? Yes. Is its inverse a function?
No.
Okay, is not a function. And we really wouldn't use function notation on it anyway because we know it's not a function. It fails the horizontal line test right here. Therefore, it is not one-to-one. Okay. Is that a function?
Yes.
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 Is this a function? No. So not one-to-one. And you should never write it that way. Please don't ever write it that way. Okay. All right. Is this one a function? Yes. Is its inverse a function? Yes. So is it one-to-one? Yes. All right.
You want to, like he's wondering if you could, yeah.
Oh, that's pretty cool. I like that. Okay. All right, so let's take a look at this second example. Here's your original function, y equals x plus 5 over 3. I'd like everyone to try to find the inverse of this. You may or may not need to graph it to tell me if the inverse and the function are both functions.
Are you subbing y for x?
No, what do I think?
Trying to soak it in with the way.
I don't think I've repeated. No, wait. You do it.
Okay. So, did you get the inverse is? You switched to x and y and you solved and you got what? 3x minus 5. 3x minus 5. Okay, any questions about that? Alright, so let's take a look at a slightly more complicated one. The next one.
Well, that's a lot of numbers.
What's wrong? I'll tell you what's wrong. I've lost all my notes. Oh, I'm good. I can do it. We don't know what this looks like, do we? Not at all. We haven't done any like this. We're going too soon. We're going to take a look at this function. What is this right here? Square root? We call this a square root function.
That's original.
Pretty, isn't it? Isn't it? Okay. Let's see if we can find its inverse, even though we don't even know what it looks like. So to find the inverse, what would I do? I'd switch, and so I'd get x equals 2 times the square root of y minus 1 minus 3. And now I need to solve for y. So what do I need to move first?
The negative 3.
Okay, let's move the negative 3. Okay, then what do I need to do?
Divide both sides by 2.
Divide both sides by 2. Great.
Square both sides.
Square both sides. I like it.
Subtract 1 from
And subtract the 1. Okay, and this is the inverse, right? We know what this is, don't we? What kind of function is this? It's a quadratic function, isn't it? We know what that is. Yeah.
Do we go in?
But let's go back to this one for a second. Now, yesterday, I actually gave you one of these, didn't we? And we talked about the domain of it.
It can't be 1.
It can't be less than 1, can it? The domain of this function starts at 1 and goes to infinity. Because if we had anything less than 1, what would we get? Imaginary. We'd have negative here. So if 1 is the smallest this could be, what's my range going to look like, guys? Negative 3 to infinity. Because if this was 1, then this would be 0, right? And the y value would be negative 3. Now, when we took our function to find its inverse, we switched the x and y, didn't we?
We did.
When we switched the x and y, we switched the input and the output. We switched the what? The domain and the range. So if the domain of g of x is from 1 to infinity, then the range of its inverse would be from 1 to infinity. Does this look like it's going to be at 1? And is this a parabola that opens up? Yeah. If the range of this function is negative 3 to infinity, what would the domain of this one be? Negative 3 to infinity. Okay, so even though we're not familiar with this one, we're going to graph it anyway. I'm going to graph this one in red. I'm going to try that again. I'm going to graph this one in red. And I'm going to graph this one in blue. In just a second. Okay, so let's graph this one. We don't know square roots, but we do know how to find like a vertex or a starting point. Where would it start?
1 over 4.
1, -3. 1, -3. Does it at least look gray?
Yeah, I can see.
Okay, okay, cool.
Start.
All right, so this is something I'm taking the square root of, right? So what is the square root of 1? 1. So can I move over 1? And then because of the 2, it's doubled. The next thing I'm going to do is go over 1, 2, 3, 4, because I can take the square root of 4, right? What's the square root of 4? 2. But I'm going to double it because of the 2. And that's what that function looks like. It's a square root function. And it looks like that. Now, I don't have to know anything about this to graph it. Because if this is my function, and I switch my x and y's to get my inverse, couldn't I just take this point right here, which is the point 1, -3, and for the inverse, switch the x and y's? So the inverse should have the point -3, 1. Okay? And this point right here is 2, -1. So this should have a -1, 2. This point is 1, 2, 3, 4, 5, 1. So this should have a 1, 1, 2, 3, 4, 5. Does it look like a reflection over y equals x? Yes. Okay, you're going, wait a second. This is supposed to be a parabola, and you only have the right side. Why?
Because that right side got translated over.
Because even though this says it's a parabola, we have this as our domain. Now, normally when we have a quadratic, what's the domain? From -infinity to, whoops, sorry guys, positive infinity. But because this was our range of our original function, it restricted the domain of the inverse. With the restriction, do they appear 1 to 1? Yes. Without the restriction, would it appear 1 to 1? No. Because we would have this other side of the graph. We good? That's a lot of good stuff right there. Okay, now, we're going to go back to our first example real quick. Now, I didn't even talk about that on the first two, did I? Look at your first two examples. The function was linear, its inverse was linear. The function was linear, its inverse was linear. What's the domain of any linear function? -infinity to positive infinity. And the domain of any linear function that's not horizontal, the range is also -infinity to positive infinity. So if we take -infinity to positive infinity and -infinity to positive infinity and switch it, does it make any difference? No. No, so there wasn't the restriction on those for the first two. That's why we didn't even discuss it. Now, we found the function f, you were given the function f of x is 2x minus 6, and we found that its inverse was x plus 6 divided by 2. Now let's add this to what we did yesterday. What if we did the composition of the function with its inverse? Or the inverse with the function? I want you to see what the result is. Please find the composition of f inverse plugged into f, and then f plugged into f inverse. Let's see what we get. so when I plug it in here, this cancels with that cancels with that, and I'm left with x. And when I plug f into f inverse, this cancels with that, and I'm left with x. Now, yesterday, when we did compositions, and we switched them, did we get the same thing out every time? No. Here, I took a function and its inverse, and when I did composition, each time I got x. Anytime you do the composition of inverses, the result will be x. And that proves, if you are asked to prove that two functions are inverses of one another, you use composition to prove. The result must equal x if they are inverses. Okay? All right, now I have a couple more examples I could do, but I think I've done enough. If you needed more examples on a particular topic, you can look in your book. The book has examples. It also has the little QR codes you could scan for the videos. You can go online. The videos can also be accessed online if you don't have a smartphone. All right, and you have the remainder of class to work on your homework. And let's talk about that homework real quick. I saw most of you come up, quite a few come up and take a picture of it. That is awesome. Your homework is out of your textbook. It's page 446. We're going to do 12, 13, 15 through 18, 20, 27, and 33 through 35. But just on problems 12, 13, 15, and 16. On these, we are asking you, in addition to following the directions, to sketch the graph of the function and its inverse, and then to tell us if one-to-one. Okay? So just on those four, those are the only ones we're asking you to sketch the graph of the function and its inverse and tell if it is one-to-one. Now, if you just sketch the function, you should be able to tell me if it's one-to-one. Because if it passes both vertical and horizontal, you're good. Okay? And that's it for today.